Hey folks, Ms. Gosling here. In this video, you're going to learn about impulse. By the end of the video, you'll be able to solve impulse and impulse momentum theorem problems. So with no further ado, let's go ahead and get started. We're going to define impulse as force times our change in time. And impulse, like force, is going to be a vector. And just a heads up, the units that we often use for impulse are Newton's seconds, so the units of force times the units for time. So let's go ahead and do an example problem. An impulse of 80 Newton seconds is applied to a box. This impulse was applied over 1.5 minutes. What is the force acting on the box? So we're going to start by listing our givens, and we know that the impulse J is equal to 80 Newton seconds. And if you're wondering, we use J to represent impulse because I is already representing a lot of other concepts, just concepts we haven't used yet. So moving forward, our impulse is 80 Newton seconds, and it is applied over 1.5 minutes. So our time is 1.5 minutes, or 1.5 times 60 seconds, thus 90 seconds. And you'll note this needs to be in seconds, because that is in seconds. Newton seconds, but I'm sure y'all understand why that's important. So again, make sure we are in our SI units when we're solving these problems. Now that we have our givens, we can list our unknown, and that is the force acting on the box. Moving forward to our equation, we know that our impulse, J, is equal to our force times our time. Thus, our force is equal to our impulse divided by our time. So plugging in our numbers to sub and solve, we get that our force is equal to our impulse of 80 divided by our time of 90, or 8/9, otherwise known as 0.89 newtons. And there you have it, guys. That is one example of an impulse problem. One thing I'm going to remind you, again, impulse is a vector, so this is in the positive direction. So that must also be in the positive direction. So moving forward to the impulse momentum theorem, because it's important to because we were talking about momentum in all these other videos, and now suddenly we're talking about impulse. In this video, we're going to learn why. So the impulse applied to an object is actually going to be equal to its change in momentum. In math speak, we say that our impulse, J, is equal to our change in momentum, P, which we can write as mass times our change in velocity, assuming, of course, that our mass is the same. So we can also, instead of writing that J is equal to our change in momentum, we could write that our force times our change in time is also equal to our change in momentum. So let's go ahead and look at some examples of how we could use this problem in practice. So, example 2. According to the Guinness Book of World Records, the fastest recorded baseball pitch was delivered by Nolan Ryan in 1974. The pitch was clocked at 109 miles per hour, and we need to figure out the impulse required to give a .163 baseball such a momentum. So I want to start, as always, by listing my givens. So I know that my pitch has my initial velocity of my baseball must be, the mass of my baseball is going to stay the same. We're not going to add any new atoms to our baseball. And so its mass is going to stay at 0.163 kilograms. I know that my initial velocity of my baseball must be 0, right? Because before Nolan Ryan starts throwing the baseball is not moving. When he finishes, however, it has a speed of 100.9 miles per hour, or approximately 45 meters per second. And we want to figure out our unknown, which is the impulse required to create this change in momentum. So writing out our equation, we're going to use the impulse momentum theorem, which is that our impulse is equal to our change in momentum. Thus, our impulse is equal to our mass times our change in velocity, or the impulse is equal to the mass times our final velocity minus our initial velocity. Moving to the sub and solve stage, we can start plugging in numbers. And what we will get is that our impulse is equal to 0.163 times 45 minus 0, or 7.3 Newton seconds. And there you have it, guys. I do want to mention, if you were given a time, so how long it took for the ball to leave the pitcher's hand, you could also figure out how much force he delivered to the ball by dividing this number by the time. So if it took, for example, 2 seconds, you would divide by 2 to figure out the force required to give the ball this change in momentum. So one last question. This one is conceptual. I have 2 balls of equal mass. One is made of clay and the other is made of rubber. Both hit a wall with the same velocity and change velocity in the same amount of time. The clay ball sticks, while the rubber ball bounces off, traveling in the opposite direction. Which ball experiences a greater force? So we have one ball that is going from having a positive velocity to a velocity of 0. And we have another ball that is going from having a positive velocity to a negative velocity. In the first case, we have a change in, so we know that the change in momentum for our rubber ball is going to be greater than the change in momentum for our clay ball, because the change in velocity for our rubber ball is greater than the change in velocity for our clay ball. So that means that the rubber ball will experience the greatest force because it has the greatest change in velocity and thus the greatest change in momentum. So let's go ahead and talk takeaways. First of all, impulse is equal to force times time, and it is also equal to the change in an object's momentum. And finally, we can decrease the force acting on an object by increasing the time it takes for that object to change directions. So this is really important when we talk about safety, right? So if we want to look at our J is equal to force times time, and therefore our change in momentum is equal to force times time, if you jump off of the 4th stair of a staircase, deciding to skip stairs 1, 2, and 3, when you land, you'll probably land by bending your knees as you land. And what this does is it increases the amount of time it takes for you to go from moving to not moving. Were you to not bend your knees, the time for that collision would decrease by a lot, right? Because you'd be going from not moving to moving, and you don't have that additional time with your knees absorbing some of that impact. So when you increase the time for a collision, the force that the objects feel is decreased. We see this a lot in safety issues around, for example, car safety, and also in safety when we look at the safety for creating gear for example, bike helmets, football helmets, any kind of helmet. A lot of the purpose of that is to protect your brain from collision, from if you hit the ground with your head, because it increases the amount of time that it takes for your head to stop moving, thus decreasing the amount of force on your brain and your skull. So with that, you now know quite a lot about collisions and about impulse, force, and momentum. So it's your turn to try solving some problems. Best of luck and happy solving.